Dear students, good afternoon to all of you. I am Dr. Dinesh Kumar, Principal Scientist from Division of Agronomy, IARI, New Delhi. Today is 14th September 2022. I think this is today is Hindi Day also. Hindi Day, our official language. So we deal with phosphorus in soil. So today we are going to discuss in the first lecture the presence of phosphorus in soil. What are different forms that are organic and inorganic? Under inorganic, what are different forms that are part? And we will see the movement of phosphorus in soil and also see different factors that affect the availability of phosphorus. So these aspects we will cover in this lecture, and followed by we will also see the related topics you can see. So overall, we are going to learn in this lecture status, forms, and availability of phosphorus in soil. Some terminology, dear students: inositol phosphate. This is very important organic compound in soil. This is also important compound in seed. When a seed germinates, it uses some energy and some food material. And inositol phosphate is very important for seed germination also. And it is also there in organic matter, and which supplies roughly whatever organic phosphorus is there. Out of that, roughly 50% organic phosphorus in this form, inositol phosphate. A cyclic molecule with 6 hydroxyl groups forms the hydrophobic head group of membrane inositol phospholipids. Inositol phosphates are intracellular second messengers in eukaryotic cells. If you are interested, you can see the structure of inositol phosphate. But for the time being, you can remember that this is very important organic compound which contains roughly 50% organic phosphorus in it. Phosphate potential. It is the chemical potential of soil that indicates the availability of phosphorus in the soil. Phosphate fixation. The process of soluble ion, that is H2PO4. H2PO4 rapidly reaching in soil to form insoluble phosphate is called phosphate fixation. So today we will see how phosphate fixation happen under different pH conditions. Phosphorus pentoxide, this is already discussed with you, P2O5. Phosphoric anhydride is another name for pentoxide, is a white, highly deliquescent solid that sublimes at 300 degrees centigrade and reacts violently with water to give orthophosphoric acid. Then phospholipids are also organic sources of phosphorus in soil, and these are esters of glycerol and are similar to structure to fats. However, unlike fats, they contain only 2 fatty acids. So before we go into the details about phosphorus in soil, just one slide on role of phosphorus in plant growth. I have already covered the deficiency symptoms of phosphorus and some roles of phosphorus, but this is just refreshing your memories. So adequate phosphorus enhances fundamental processes of photosynthesis. If sufficient phosphorus is not there or sufficient supply is not there, the photosynthesis will be affected adversely. Flowering, fruiting includes your seed production. All these will be affected by short supply of phosphorus. And you can understand the value of photosynthesis and flowering, necessary in large amounts for cell division and growth in meristematic tissues. Root growth is very important, and particularly lateral roots. So lateral root formation are significantly helped by phosphorus. So therefore, for root development, phosphorus is necessary. Good supply is essential for efficient biological nitrogen fixation, and resulting growth and protein content of legumes. As many of the students are aware that in leguminous crops, our pulses, forage legumes, or grain legumes, the rate of application of nitrogen is normally 20 to 25 kg per hectare, just as a starter dose. But if you see the quantity of phosphorus or requirement of phosphorus by legumes, it is generally 40 to 50 kg P2O5 per hectare. You can convert it by dividing this value by 2.29. 2.9 to 2.29, if you divide P2O5, you get P. Or multiply P by 2.29, you get P2O5. So larger quantity of phosphorus are applied or required by legumes. So why it is required? Because it helps in the development of roots and also largely photosynthesis. It is important. And you can see there are many experiments. I have seen some papers where nitrogen was applied under two plots, but in one plot phosphorus was not applied. In another plot, nitrogen and phosphorus both were applied. So N fixation was sufficiently higher under plot where N and P both were applied. That means phosphorus has very important role in nitrogen fixation also, biological nitrogen fixation. So far, soil fertility is concerned. If you remember, it is you are adding some nutrients or some essential nutrients are supplied. But so far, fertility related to phosphorus is concerned. It has got three major problems. One problem is the total P content of soil is relatively low compared to nitrogen, calcium, or sulfur. The total P content of soil is relatively low, ranging from 500 to 10,000 kgP in the upper 50 centimeter of 1 hectare of soil. P compounds commonly found in soils are mostly unavailable. The second problem of phosphorus fertility is that the compounds which are there in the soil are mostly unavailable to the plant uptake. They are not in readily available form. If they are there, the quantity of phosphorus is too little, too small in the soil solution. When soluble phosphorus added through fertilizer, if you are applying fertilizer from outside or manure from outside, which contain some quantity of soluble phosphorus that is quickly converted into unavailable form or fixed forms. So there are three problems of phosphorus related to soil fertility. One is relatively low content in soil. Number two, that most of the compounds in soil are having phosphorus in unavailable form or insoluble form. And thirdly, when you supply it through fertilizer or manures, it is quickly converted to unavailable or insoluble forms. So these are the three important problems related to phosphorus fertility. Now let us see phosphorus in soil. As I told you, that the quantity of phosphorus in soil is very low. So total phosphorus in soils is generally less than total N or K. Just now I told you, even it is less than sulfur as well as calcium. 1/10 to 1/4, 1/10 to 1/4 of nitrogen and 1/20th of K. So you can see the proportionate content of phosphorus in soil. This is total phosphorus. Total phosphorus in surface soil may be from few milligram to 1 gram per kg. So this is the range. Unlike nitrogen, phosphorus in subsoil may be less than, equal to, or greater than surface soil. So far nitrogen is concerned, it has more concentration in surface, soil surface. As far as phosphorus is concerned, it may be in subsoil, it may be less than the surface soil, or in subsoil, it may be equal to surface soil, or sometimes in subsurface soil, phosphorus can be greater than surface soil. So it is quite interesting fact. So far, total phosphorus in soil is concerned, it has two components, organic phosphorus and inorganic phosphorus. So on an average, you can say that 50% phosphorus is in organic form and 50% is in inorganic form in soil. So these are very general figures. However, they will vary. Sometimes it may be 60% organic, 40% inorganic, and vice versa. So it is not fixed. What I told you is average value. Now, before we understand the phosphorus cycle and things, one term will come that will confuse the students. That is occluded P, occluded phosphorus. What is it? It is if iron or aluminum hydroxides are precipitated on the surface of iron and aluminum phosphate. See, iron and aluminum phosphates are already there, suppose, and on them you get iron or aluminum hydroxide attached. The phosphate becomes occluded. Occluded means its solubility is further reduced. Occluded secondary inorganic phosphate. So that is your occluded phosphorus. Means phosphorus in the form of iron and aluminum phosphate is encircled by iron or aluminum hydroxide. Then it is called as occluded phosphorus. Now you see the phosphorus cycle of phosphorus in soil. This is not exactly cycle. It is just, you can see different forms of phosphorus in soil. So suppose there is solution phosphorus. In the solution phosphorus, you will have H2PO4 and HPO4. Only two forms can be taken up by plants. Two inorganic forms can be taken up by plants. Phosphate, triphosphate, it cannot be taken up by plants. It is only H2PO4 -1 and HPO4 -2, monovalent, divalent. These forms can be taken up by plants, and these are in the soil solution. So now question comes, when plants take up phosphorus, where from it will be buffered? It will be replenished. So labile adsorbed phosphorus can come to solution phosphorus, or labile organic phosphorus may also come to the soil solution, and it can also become insoluble. So they are in actually equilibrium. All these kind of phosphorus are in equilibrium. And then you can see some of the solution phosphorus can become insoluble phosphorus compounds, or some insoluble phosphorus compound can contribute towards soil solution, depending upon the condition of the soil solution. And then you can see very interestingly this labile adsorbed phosphorus. Labile adsorbed phosphorus is quickly available for the plant, but it can become occluded phosphorus. Occluded phosphorus. So this is how you can see. And then labile organic phosphorus. Labile organic phosphorus has come from stable humus. So sometimes humus also break down, and whatever phosphorus is there, it is released slowly, and then it becomes labile organic phosphorus going to the soil solution. So this is these are different forms and very simple transformation of phosphorus in soil. Now you see inorganic phosphorus compounds in soil. Just now you have seen some organic. I told you organic is mostly this inositol phosphate. I'll show you. So in alkaline soils, you know, the calcium compounds of phosphorus dominate, and in acidic soils, iron and aluminum and also manganese phosphates dominate in acidic soils. Now, dear students, this is very important for you to see this table. Can you see it properly or not? I don't know.
Yes, sir.
Yes, sir.
You can see it. So this is inorganic phosphorus containing compounds important for soils. I just copied from Brady book. I suggest repeatedly you read phosphorus from Brady book, or also from soil and fertility fertilizer, soil fertility fertilizer, and just you will find very interesting writings about a topic. Now you see in each group the compounds are listed in the order of increasing solubility. You can take first group, iron and aluminum compounds. So the name of the mineral is stengite. So this is ferrous sulfate or ferric sulfate, FePO4, 2s2. Is it ferric phosphate or ferrous phosphate?
Ferric, sir. Ferric.
Ferric phosphate. Why?
Sir, PO4 minus 3 will be balanced by Fe plus 3.
Good. If you have 3 valency of iron, then it is ferric. If you have 2, then it is ferrous. Good. And then the next one is less soluble. In these two, ferric phosphate is more soluble than aluminum phosphate. So aluminum phosphate mineral is very slight. Then these are in acidic conditions. These are in acidic condition. If you go to alkaline conditions, you will find some calcium compounds. They are insoluble, practically they are insoluble. But as we move from top to down, top to bottom, their solubility increases. Solubility increases. And you must remember these formula. Here I wish to tell you that apatites, apatite is the most important mineral which is mined. So some phosphate rocks are there. Morocco have highest reserve of rock phosphate. And this rock phosphate or phosphate rock, they are used interchangeably. Phosphate rock or rock phosphate. So phosphate rock, when it is there in the rock, so phosphate rock contains mostly phosphorus in apatite forms. Apatite forms, and nearly 70% of world's apatite reserve or phosphate reserves are in Morocco. So Morocco has the highest quantity or amount of phosphate rock reserves. And second point is that these reserves are very finite. I do not know, but maybe in next 50, 60 years, these kind of reserve can exhaust. And then it will be difficult to make fertilizers, phosphatic fertilizer. For your information, all the fertilizer, phosphatic fertilizer in the world are manufactured by apatite. So this apatite mineral is very, very important. And it is also found in soil under calcareous conditions, or when your pH is high, alkaline soil is there, then your monocalcium phosphate converts to dicalcium, tricalcium, and finally this apatite forms, which is most insoluble. It is most insoluble. Now coming to apatite, they have variety of apatite. If fluoride is there, then it will be fluorapatite. If carbonate is there, it will be carboapatite or carbonate apatite. If OH2 is or hydroxyl is there, then it is hydroxyapatite. And similarly, if calcium oxide is there, then it will be oxyapatite. And after apatite, it comes tricalcium phosphate. Tricalcium phosphate is also there besides apatite. Tricalcium phosphate is also there in our bones and teeth. And then octacalcium phosphate, and then dicalcium phosphate, monocalcium phosphate, magnesium compounds, and then is2-white. So is2-white has really more solubility, and it can give phosphorus most easily. Is2-white can give phosphorus most easily because increasing order of solubility. Now I come back to fluorapatite. Many of you might be knowing the formula. Every student must remember this formula. Fluorapatite, 3Ca3PO4 twice CaF2. And by nature, most of the, this is the dominating apatite. Fluorapatite is the dominating apatite, means it is in larger amount in the world compared to other apatites. Then you get carbonate apatite, 3Ca3PO4 twice CaCO3. That means 3 molecules of calcium phosphate are joined together, and one calcium is also there. So there are total 10 calcium here. And 1 calcium is also attached to this tricalcium phosphate. So problem is to break down this bond, break down the bond between tricalcium phosphate and calcium fluoride. Here, if this bond is broken down, it can be broken down by heat or high temperature, or it can be broken down by acids. Some acids can be employed to break down the bond between tricalcium phosphate and calcium fluoride or calcium carbonate. So here you need some energy, some form of energy or chemicals, because all the phosphatic fertilizers are to be manufactured from these appetites. So is it clear, or you have any doubt in this? Inorganic phosphorus containing compounds important for soils. They are in soil also, but they are mostly there in the mines or phosphate in the form of phosphate rock. Now coming to organic P, you have seen different forms of inorganic P in soil. Now see organic forms. So organic phosphorus found in plant residues, manures, and microbial tissues. Soils low in organic matter may have only 3% of their total P as organic P. Very small contribution of organic P out of total P. But high organic matter soils may have 50% or more of their total P as organic P. So some soils can have 97% inorganic P and only 3% organic P. But some soils can have 50-50 also. And organic phosphorus can be few milligrams to 0.5 gram per kg. Dear students, I have taken most of the things from Brady book, Nature Properties Soils, and Soil Fertility and Fertilizer. If you miss anything, you can consult that book. Everything is given in detail. So now you can see forms of organic phosphorus in soils. Inositol phosphate. Inositol phosphate is most important, and its content in soil may be 1.4 to 356 milligram per kg soil. And by percentage, it can be 0.3 to 62% of the total organic P. Or roughly, I told you 50%, whatever organic P is there. In this, 50% is contributed by inositol phosphate. Then comes nucleic acids. Concentration may be 0.1 to 97 ppm. And percentage-wise of organic P, it can be 0.1 to 65%, depending upon the organic matter content in the soil. It is so simple. As you increase the level of organic matter in soil, so will increase the phosphorus and nitrogen. Then phospholipids can have 0.4 to 17 ppm and percentage-wise 0.03 to 5.4%. This is by Harrison, 1987. Now see, this organic phosphorus content in soil will depend upon climate, means factors that affect accumulation of organic matter in soil. They will also affect phosphorus, organic phosphorus content in the soil. So factors like climate here, your rainfall, your temperature, and so on, they will affect the P content in soil, organic P content, vegetation, soil texture, land use pattern, fertilizer practices, drainage practices. For details, you can consult the book. How this organic phosphorus content is depending on these factors. Now you see classification of phosphorus compound in soils. How they are classified? There are three major groups. One is readily available phosphorus. Readily available phosphorus is in soil solution, and divalent phosphate HPO4 2-. This is divalent and monovalent H2PO4. You can call them orthophosphate or phosphate ion, whatever you like. They can be called orthophosphate phosphates. Released from other forms or added in fertilizer or manures. So these readily available phosphorus is in soil solution, and it is HPO4 and H2PO4. Here I wish to tell you some part of phosphorus is also absorbed in organic form. Some soluble organic compounds, soluble organic phosphorus compounds are also taken in the form of molecules by phosphorus. Some organic phosphorus is going directly into the plant. And then where from this readily available phosphorus is coming? So slowly available phosphorus, labile phosphorus, this will contribute towards readily available phosphorus. So for example, iron, aluminum, and manganese phosphates, those were fixed. They are in equilibrium with this readily available phosphorus. They will supply it in acidic soils. And in alkaline soils, calcium magnesium phosphate are labile kind of phosphorus, and they will supply to the soil solution. And then freshly precipitated or held on surface of fine soil particle. So some of the phosphate can be freshly precipitated, and they can also supply to the soil solution. Now, where from this labile phosphorus will come? This labile phosphorus will come from non-labile phosphorus. So this is known as very slowly available phosphorus or non-labile. Spelling is wrong. It can be labile, L-A-B-I-L-E. These are the precipitates of iron, aluminum, manganese, and phosphate, but they are aged. They are aged. Once they are fresh, they are labile. If they become aged, then they are very slowly available. Phosphorus, non-labile. Precipitates of iron, aluminum, manganese, and phosphate, aged and well crystallized. So they are non-labile. Penetrate soil particle and they are stable, but they are in equilibrium with labile phosphorus. Now see some more characteristics of these labile and non-labile forms, and also soluble phosphorus. So relative plant availability and extractability of inorganic phosphorus from forms in soil. Dear student, I tell you, this is very interesting, very scientific topic, phosphorus in soil, phosphorus in fertilizer. So hope you will enjoy and have your concentration on this. So now you see, just now I have shown you a soluble phosphorus or phosphorus in solution, H2PO4, HPO4. And then it gets some phosphorus from weakly adsorbed phosphorus, and this is in equilibrium with strongly adsorbed phosphorus, and then mineral phosphorus. This is in tricalcium form or octacalcium phosphate, or maybe apatite. Here it is level of apatite. It is aged or non-labile, and this is labile. This is kind of labile, and this is your available or soluble or in the soil solution. Is it clear? This is available, this is labile, this is non-labile, and this is insoluble. You can say insoluble. So P form or source. So this is basically soluble P, and weakly and strongly adsorbed. This is phosphorus adsorbed to clay and other mineral surfaces. It is just on the surfaces, but then it has become a very insoluble compound, calcium, iron, or aluminum phosphate, minerals, and very strongly adsorbed phosphorus. Now see extractability by soil test. How easily they can be extracted by extractants. So this can be high. This can be simply extracted by water, and then weakly adsorbed. It is also high extraction. High extraction means it will tell you the level of the phosphorus and also how much will be made available. Then strongly adsorbed, very low extractability, and very low and very low. See availability to plants, very high, high, low, and very low. Very simple graph or P cycle in plant soil system. I am showing you just in the very simplest form, a soil solution, and then it is in equilibrium with readily available pool, less readily available pool, and very slowly available pool. The solution P can go for crop uptake, and crop uptake it can remove in the harvested produce, and it may come from within the soil like this, or water soluble nutrients or fertilizer or manures can be added that contain water soluble phosphorus. Now see some more simplified way of this. Same thing, almost available soil P, that is solution. Here organic matter can supply, or organic matter are your crop residues, and they also contain a small fraction of soluble phosphorus that can straightway become part of the soil solution or via decomposition. This organic matter will decompose or mineralize. Mineralization will result in available phosphorus. Similarly, in the soil, within the soil, there are P-bearing minerals like apatites, etc. They can supply on mineralization. They can supply to the solution. and then some of the available soil P, which is in the solution, can go for fixation also. Fixation, and then it can become part of P-bearing minerals. But among all these cycles, I suggest you don't bother about what I am showing here. You consult book of Brady and see page number 671. On page number 671, you will find phosphorus cycle in soils. So this explains you much in a much simple way and much better way. So hope you will see it, this phosphorus cycle in soil in the Brady book yourself, because from here you cannot see what is written on this picture. But this is very simplified diagram. Everybody can understand. Phosphorus cycle in soil. Let us start phosphorus in soil solution, means available phosphorus. So compared to nitrogen, sulfur, calcium, concentration of phosphorus in soil solution is very low, available phosphorus. And at one particular point of time, out of 100 units of phosphorus, only 0.5 or 0.5% phosphorus is your available phosphorus, is in soil solution. So you can see out of 100, only 0.5% is available or soluble phosphorus. So compared to other elements or macronutrients like nitrogen, sulfur, calcium, concentration of phosphorus in soil solution is very low, maybe 0.001 milligram per liter in very infertile soils. Low fertility soils, it is range, and in heavily fertilized soils or soils which are rich in fertility, they can have about 1 ppm of the available phosphorus, or 1 milligram per liter. Phosphate ions, these are HPPO4 2 minus. 2 minus is the valency. So here it is not in superscript. I could not make it, but you can consider it how to write it correctly. And H2PO4 minus 1. In H2PO4, you have -1. If it releases one hydrogen, then it becomes HPO4 2 minus. One more charge is increased if you remove one hydrogen from here. So phosphate ions and soluble organic phosphorus. You can see soluble organic phosphorus compounds are taken up by plants. This is copied from Nature and Properties of Soils. The chemical species of phosphate ions in solution is decided by the pH. Chemical species means whether it will be H2PO4, PO4 or HPO4, it is to be decided by pH. Phosphorus in soil continues. In strongly acid soils which have pH of 4 to 5.5, monovalent anion, that is H2PO4 minus 1, dominates when pH is 4 to 5.5. Alkaline solutions means above neutral, this divalent HPO4 minus 2 or 2 minus dominate under alkaline or alkaline pH, means more than 7. Both anions are important in near neutral soils, soils which are near neutral. H2PO4 minus 1 is thought to be slightly more available, slightly more easily taken up by the plant. So ease in taking is more for H2PO4 minus 1 than HPO4 minus 2. Means monovalent would be preferred by the plant over divalent. Besides low presence in soil solution, phosphatic ions or phosphate ions are also quite immobile. That is interesting fact. You know, it comes to the plant root by diffusion process. So they are really quite immobile, less mobile in soil because they react strongly with components on the surface of the soil particle. When they move and they find something to be fixed, and then they are very fast in reaction actually. So they can react and they will not move. So they will convert into immobile form. Thus, leaching losses are generally quite small. So in case of phosphorus, the phosphorus loss from soil happens only by two means. One is by crop uptake. The plants will remove phosphorus from the soil and then you will harvest the plant biomass and take away from the field, then this is one way to lose phosphorus from soil. And other means is just by erosion. Soil erosion can remove phosphorus like any other nutrient. Soil erosion will not see that it is phosphorus or potash or zinc there in the soil. It will take everything, whatever is there in the top layer. Erosion will remove the soil particle. So for phosphorus loss, these are only two mechanisms. There is no tension of denitrification or means it will not volatilize, it will not leach also. Leaching is very, very insignificant. So thus, phosphorus have residual effect. Sometimes it gets accumulated in fixed forms, whether organic or inorganic, it gets fixed and it can be released to the next crop from the residual fertility. Now we will discuss this picture. We can discuss at lower pH values, more hydrogen ions are available in solution. So you can see this picture, very interesting picture. pH of the solution. On x-axis, it is the pH starting from 0, 1, 2, and up to 14. And you can see the phosphate forms. First, you see on the y-axis, it is the concentration, percentage among these four. Suppose you make the total of these. See, they are 100 grams. Out of 100 gram or 100 units, what proportion is there? What proportion is there for H3PO3? So see, at near 0 pH, at lowest pH, H3PO4 almost 100%. Up to 1 pH, you can see it is mostly H3PO4 form. And as you move towards right side, the H3PO4 decreases. As you move more and more, and near 4, when you come at 4, I think it is over. Now you will not find any significant quantity of H3PO4. This is phosphoric acid. So we move to next link, and then I will continue discussing this picture. So coming back to this picture, you can see at pH 4 almost it is over. This form is over. It has no level. Then you see H2PO4. The next form is H2PO4. It is most preferred by the plants. And you can see the levels at in the beginning it is not there, but when you come around 1 pH, so very little quantity of phosphorus there in the form of H2PO4, and then it increases. And at this level, it is 100%. So you can see starting from pH, say around 4 or something, and up to 6 or something, you can see it is mostly H2PO4. And then comes the turn of HPO4. You can see here it is 0, and then as at about 6 pH, now you will see that HPPO4 2 minus is also starting increasing its level. So you can see it is increasing, and at this pH around, you can see that around 8 is maximum. Around 8 it is maximum. You can see 100%, and then it stays up to pH 10 or 11. You can see 10 or 12. It is like this HPO4 form, and then comes your phosphate. Then this H will be removed, and phosphate at 10 pH. You can see 10 pH, there is no PO4 3 minus. But then after 10, you can see it starts increasing. It starts increasing. Even at 14 pH, you will get a little HPO4, not much, but you can see this is HPO4. So around 13 pH, it will be just 10%, and at 12 pH, your HPO4 will be this, and you can see this side. So it is easy to understand this picture. If you can understand this picture, get the inferences from this picture. So inferences are, at lower pH values, more hydrogen ions are available in solution. Phosphorus ion containing more hydrogen predominate, like H3PO3 or H2PO4. More the hydrogen, they will dominate in acidic pH. Near neutral soils, HPO4 2 minus and H2PO4 1 minus are found in nearly equal amounts at near neutral pH. And I have seen in many books that they say that at pH 7.2, you get equal quantity of H2PO4 and HPO4, equal quantity, 50-50. Whatever available phosphorus is there, in that 50% is it H2PO4, 50% HPO4. So both species are readily available for plant uptake. Now, P movement in soil, as I told you that it moves very slowly. It is practically less mobile or immobile nutrient in soil. So soluble phosphorus either from fertilizer or from natural weathering or from soil itself reacts with clay, iron and aluminum compounds in the soil and converted readily to less available forms by fixation, which is known as phosphorus fixation. Thus, its movement is very slow. It starts moving, then on the way, it gets fixed. So little quantity of phosphate, H2PO4 or HPO4 may reach the soil solution. Now, because of these fixation processes, phosphorus moves very little in most soil. The data says that it moves less than an inch in most soil. An inch means 2.5 centimeter. So it moves less than 2.5 centimeter, not more than that, and that is mostly by diffusion. Thus, little soil phosphorus is lost by leaching. There is no free H2PO4 or not much free HPO4 to be lost by leaching. This fixed residual phosphorus remains in rooting zone and will be slowly available to the succeeding crops. Therefore, it will have some residual effect. P movement in soil continues. Crops seldom absorb more than 20% of fertilizer P during first cropping season after application. So on an average, fertilizer recovery from water-soluble fertilizer, recovery of phosphorus is 15 to 20%. Remaining 80% will remain in soil or will be lost by erosion, partly lost by erosion, or little bit by leaching. Soil erosion and crop removal are the significant ways of soil P loss. It stays close to the place of origin. Wherever you put it, it will remain there. It does not like to move. It is very lazy element or lazy nutrient. Nearly all phosphorus in soil moves by diffusion, and diffusion depends upon soil moisture. Now you can see the relative nitrogen, phosphorus, and potassium and calcium movement in soil. This is relative. So you can see within the soil, nitrogen moves the maximum. Proportionate, it is in proportion. So nitrogen moves highest in the soil. Number 2 is potassium. And number 3 is calcium. And number 4 is phosphorus. So you can see the relative movement in soil. Now, soil phosphorus, since the roots of growing crop contact only 1 to 3% of the surface, 15 to 20 centimeter depth. So that means the minimum, very low volume of soil is occupied by the roots, or in the contact, roots are only up to 1 to 3% soil volume contact of the soil volume. So soil must be adequately supplied with phosphorus to support optimum growth. So that means that roots cannot go into all the particles of the soil, all the parts of the soil. They cannot touch, they cannot reach to the phosphorus of whole soil. They can reach the phosphorus of the whole soil up to 1 to 3%. So therefore, your root growth should be encouraged if you want to improve the phosphorus uptake and use. Or otherwise, you place the phosphorus fertilizer or source near the roots, so uptake is improved. The soil phosphorus level throughout the root zone should be high enough to ensure adequate available P. Adequate available P should be available at every growth stage of the plants. So in the beginning, when people were making some recommendations, they used to say that plant accumulate 2/3 of its phosphorus requirement during 1/3 of its life cycle. These were very general statements made by people. I repeat it, that plant, whatever uptake of phosphorus is there by plant, 2/3 P uptake is achieved by plant when it completes 1/3 period of its life cycle. But those things have proved wrong. Plants like maize or many other plants, they take up phosphorus even up to harvest or up to maturity stage. So there is no such statement, no such statements are not correct. So it is required throughout the growing period of the crop. The phosphorus level throughout the root zone should be high enough to ensure adequate available phosphorus. This I have already read. Now we come to the most important part of this lecture, that is factors affecting phosphorus availability. As you have seen, that very small quantity of phosphorus is there in the soil solution. So if you want to replenish the uptake, the phosphorus that has been removed by uptake, then continuous supply of the phosphorus should be there to the soil solution. And now we are going to see the factors affecting phosphorus availability. The same factor will affect the retention or fixation. So students can be asked 3 questions in your exam. What are the factors that affect the phosphorus availability? Number 2, it can be asked, what are the factors that affect the retention of phosphorus in soil? And third question can be, what are the factors that affect the fixation of the phosphorus in soil? So answer will be same. The factors will be same. Only thing is how you write it. Suppose you are writing retention or availability, then the same factor will say that, for example, soil pH. Soil pH, the ideal pH, you can say that ideal pH, you will get more availability of the phosphorus. And when it is fixation, so you can say at lower pH, it gets fixed. With this, at higher pH, it gets. So only thing is that how you write it. But the factors will remain same. So we will see how these factors affect availability, retention, or fixation of phosphorus in soil. More the fixation, less is the availability. More the fixation, less is the availability. More is the availability, less is the fixation. So factors like soil pH, amount of clay, type of clay, time of fertilizer application or source of fertilizer application, soil aeration and compaction, soil moisture and temperature, phosphorus status of the soil, type of crop or type of varieties, other nutrients, interaction with other nutrients, amount and recommendation of soil organic matter, decomposition of soil organic matter, and activities of soil organisms. So these are the important factors that affect the availability of phosphorus. So overall, these factors can be grouped into factors like climate. Climate may be your vegetation, maybe your temperature or rainfall. They will affect the availability of phosphorus. Similarly, crop characteristics, crop variety. Some crops are efficient user of phosphorus, some are not. Similarly, varieties. So then there can be soil factors like pH. pH can affect, anion exchange capacity can affect phosphorus availability. And in soil, you got clay, composition, aeration. So many factors related to soil can affect phosphate availability. It is just your thinking. If you give thinking, you can find the answer. Next is your fertilizer factors, means source. Source will affect the availability. We will discuss how the source of fertilizer will affect the availability, discuss in detail. Maybe your time, method, rate of application. So these are the factors, you can summarize them. And now we start with soil pH. You have already seen where was the maximum availability of phosphorus in that picture. Phosphorus, available phosphorus means H2PO4 and HPO4. So here you can see ionic forms of inorganic phosphorus depends on soil pH. So you can see here that phosphate is at pH 10 or more. It is dominating here. And HPO4, divalent, HPO4, it dominates at pH 8 to 10. And both are roughly equal HPO4 and H2PO4. Roughly they are equal, and it is about 6.5 to 7.5. And then comes the H2PO4. H2PO4, you still decrease the pH, then it will be H2PO4 from pH 4 to 6, and then H3PO3, phosphoric acid, pH less than 3. So these are actually dominating forms. However, they can overlap. Means at this pH, it will be dominating. Means most of the P will be in this form. Similarly like this. So you can see this picture and it affects your availability. So you can see maximum availability is in this part, 6.5 to 7.5. And at pH 7.2, both the forms are equal. Now see how this soil pH is affecting the fixation of phosphorus. What are the different means of fixation? So generally, less fixation, more availability. More fixation, less availability. So inorganic fixation of added phosphorus means when you are applying phosphorus to the soil, what are different routes of this particular fertilizer? Suppose you have used DAP or MAP or SSP. Then what will happen to it at various soil pH? Average conditions are representative. So these are average conditions, and any particular soil would have a somewhat different distribution. So again, it is just a generalized picture to have some understanding. However, the exact fixation will vary with the kind of soil and climate and other factors. So in this case, you can see on x-axis, it is the pH, soil pH. So soil pH is increasing. As you know, when we move from left to right on the axis, the values increase 4, 5, 6, 7, 8. And on this y-axis, we have distribution starting from 0, 20, 50, and 100%. So now you can see when pH is low somewhere around 4 and up to, you can say 4.5 or 5. The fixation can happen, chemical fixation by soluble iron, aluminum, and manganese. So here you have lot of iron, free iron, aluminum, and manganese. So that can make their respective phosphates at this lower pH. And you can see the proportion up to this. Up to this, it is say about 50, 60, 40% at this very low pH. As you increase the pH, the values decrease, the fixation decrease. Similarly, simultaneously, this is the proportion for fixation by hydrous oxides of iron, manganese, and aluminum. So they fix very large quantity. And you can see at 5 pH, very high, and up to this. And at pH 5.4 or 5.3. So you can see next fixation is by hydrous oxides of iron, manganese, and aluminum. And then this small strip, you can see reaction with silicate minerals. They can react with silicate minerals, and this much of fixation or proportion is there. Relatively available phosphorus, available phosphate. So you can see here, it starts availability at somewhere around after 4.5, and you can see maximum availability is between 6 and 7. 6 and 7, and it further decreases. So this is your available phosphate. And then fixation mostly as calcium phosphate. As pH goes in alkaline conditions, so you can see at this, so this much, say you can say more than 95%. 95% is here is your calcium phosphates. So this is how fixation happens by soil pH, under acidic pH and basic pH. Precipitation of phosphorus as slightly soluble calcium phosphate occurs in calcareous soils with pH 8. So if your pH become 8, then you will have calcium phosphate precipitation. Under acid condition, phosphorus is precipitated as iron or aluminum phosphate of low solubility. Here manganese can also be there. Maximum availability of phosphorus generally occurs in a pH range of 6 to 7. This is one of the beneficial effects of liming. If your pH is below 5 and you want to increase the phosphorus availability, then you can add lime. Now, maintaining a soil pH in the range 6 to 7. So you can see slightly acidic conditions are good for phosphorus availability. 6 to 7 also favors the presence of H2PO4 ions, which are more readily absorbed by the plant than HPO4 minus 2, which occur at pH value above 7. So you can see how under acidic conditions, how this phosphorus is fixed or becomes unavailable or insoluble. Al3 plus H2PO4 monovalent, it is soluble phosphorus. In the presence of water, hydrogen ions are released and you get this AlOH2 H2PO4, aluminum phosphate. Then it is your insoluble. So H2PO4 ions with dissolved iron, aluminum, and manganese ions to form insoluble hydroxy phosphate precipitates. So they can make hydroxy phosphate precipitates. So this is Mn3 and Mn3 is correct or is it incorrect? What are the valencies taken by manganese? Anybody idea? This Mn3 is correct or is it incorrect?
Correct, sir.
Correct. Okay, but I was confused. Is it 4 or 2 is there? Mn2 is also there. 2 plus is there. So 3 is also there. You tell me, is it 3 or 4? Kindly check it. I missed this point, whether it is 3 or 4. You can check it. Now go to next. In alkaline soils, pH 8, soluble H2PO4 quickly reacts with calcium to form a sequence of products of decreasing solubility. So you can see here, monocalcium phosphate, H2PO4 twice, H2O plus 2H2O. So you can see it in the presence of calcium carbonate, more calcium is added to it, and it is converted to dicalcium phosphate. Means monocalcium phosphate has converted to dicalcium phosphate, and CO2 is released. And this dicalcium phosphate, by further reacting with calcium carbonate, is making tricalcium phosphate. And this is very, very insoluble. And then CO2 is released. So students must learn these reactions. These reactions, simple reactions, but they are very, very important. When you write your answers in exams, if you write these reactions, your answer become more interesting. Examiner, evaluator will be interested to know these reactions. So you should remember these very simple reactions for your exam purpose. So after pH, now you have seen that at which pH you get more fixation, more retention, and at which pH you get more availability. So therefore, role of pH is most important in deciding the availability of phosphorus for the plants. Now, next factor affecting availability of phosphorus is amount and type of clay. How much is the quantity of clay? Generally speaking, your fine texture soils, such as clay loam soils, have a greater P-fixing capacity than sandy coarse texture soils. So fine textures or heavy soils will fix more phosphorus than light texture soils or sandy soils because of their clay content, more clay in fine texture soils. Clays of type 1:1, that is kaolinite, have a greater phosphorus fixing capacity than the 2:1 type of clays. Soils dominating with kaolinite will fix more phosphorus than soils which are dominating with more morillonite, elite, or vermiculite, which are 2:1 type of clays. Soils formed under high rainfall and high temperature contain large amount of kaolinitic clays under high rainfall areas or high temperature area, exactly tropical wet kind of climate, and therefore have a much greater fixing capacity for phosphorus than soil containing 2:1 type of clay. So normally these 1:1 type of clay is found in soils with high rainfall area and high temperature. High temperature and high rainfall also increase the amount of iron and aluminum oxides in soil, thus higher P fixation. So these are classical examples. These classical examples are available in Eastern India, in Assam or in Orissa or some other areas. Now you see soil components responsible for phosphorus fixing capacity are in the order of increasing extent and degree of fixation. So you can see 2:1 type of clays fix the lowest quantity of phosphorus. The next in the order is 1:1 clays. They fix more phosphorus than 2:1 type of clays. Then carbonate crystal still fix more than the previous one. Then crystalline aluminum, iron, manganese oxide, and then amorphous aluminum, iron, and manganese oxide, allophane.
हेडसेट का फोन आया था मिलने के लिए क्लास के
मेरे लिए
हाँ
ठीक।
मेरे को ऊपर फोन आया था
ठीक है, मिल लो
मैं-
मिल लो. So you can see here amorphous aluminum, iron, and manganese oxides fix the highest quantity of phosphorus and least by 2:1 type of clays. So this is individual fixing capacity. Time and source of phosphorus application. Fixation of soil P increases with time of contact between soluble P and soil particle. More the time, more is the fixation. Consequently, more efficient utilization of fertilizer P is generally obtained by applying the fertilizer shortly before planting the crop. There is no need to apply phosphorus 1 month before the sowing. It is better to apply phosphorus on the same day, because if you apply 10 days, 15 days before, most of the P will be fixed and will not be available to the crop. So therefore, apply phosphorus when you are going for planting or sowing of the crop. Similarly, method of phosphorus application, you can see bending. Bending of fertilizer for row crops increases efficiency of fertilizer P on soils of high P fixing capacity than soils of low P fixing capacity. If your soil is having high phosphorus fixing capacity, in that case, bending is always desirable, because by doing or by applying fertilizer in bands, the fertilizer will contact the minimum volume of the soil, or fertilizer will remain in the minimum contact of soil particle. If you broadcast it, then it is mixed in the soil, then it contacts larger volume of soil, and it is in the contact of more soil particles or clay particles. Thus, fixation will be more when you broadcast and mix it in the soil. Particularly, water-soluble phosphatic fertilizer should not be mixed or broadcast in the soil. It should be band applied. So to improve the efficiency, so efficiency of band applied water-soluble fertilizer will be more than broadcast applied fertilizer. The fixation of phosphorus from SSP and readily available P fertilizer. Readily available P fertilizers are your single superphosphate, triple superphosphate, monoammonium phosphate, diammonium phosphate. So they have almost more than 90% phosphorus as water-soluble phosphorus. So they are already, means phosphorus in those fertilizer is in available form. So these SSP and readily available P fertilizer will be proportionately greater as compared to rock phosphate and other slowly available fertilizer. So fixation will be much higher in case of water-soluble fertilizer if you broadcast them compared to rock phosphate. Friends, rock phosphate has 0% available phosphorus. It does not have phosphorus in available form. It is, as you know, this rock phosphate contains phosphorus in octa, this not octa, this is apatite forms. So apatite is even citrate insoluble. So this is not soluble even in citric acid. Therefore, it is 0% phosphorus available. So in that case, the phosphatic fertilizers, insoluble phosphatic fertilizer like rock phosphate should not be band applied. It should be properly broadcast into the soil. First thing is that it should be powdered well. Make very fine powder of rock phosphate, and so that the particle size is more and the surface area is also, particle size is small and surface area, total surface area will increase. So that is why you should broadcast this fertilizer into the soil, mix it into the soil so that it comes to a greater volume of soil particles. Then the solubilization, here you want to solubilize it so that you mix it into the soil. So for insoluble fertilizer, broadcast is always desirable and better. Now, soil temperature, aeration, these physical factors like moisture, compaction, they all affect phosphorus availability. So far temperature is concerned, P absorption by plant is decreased by low soil temperature and poor soil aeration. So naturally, you know that phosphorus uptake movement is also governed by temperature. So optimum temperature, under optimum temperature, you will have maximum availability and uptake of the phosphorus. Excess soil moisture or compaction reduces soil oxygen supply. So excess soil moisture means waterlogging conditions or compaction by machinery or by some other means reduces soil oxygen supply. That is the problem, and it results in decreased ability of the root to absorb soil phosphorus. Compaction reduces aeration and pore space in root zone, thus reduces P uptake and plant growth. Compaction also decreases the soil volume that plant roots penetrate, limiting their total access to the soil phosphorus. Because phosphorus is not moving in the soil, not much mobile. Therefore, we want root growth, more root growth. So under compaction, aeration will be less and root growth will be less. So the uptake and availability of phosphorus will be less. Roots also have help in the solubilization of fixed phosphorus by releasing root exudates. So lower the root mass, lower will be solubilization of phosphorus. Increasing moisture to optimum levels make phosphorus more available to the plants. Phosphorus status of the soil also affects the fixation or availability of the phosphorus. Crop responses to fertilizer P will be greater and more frequent on soils testing low in P. Means if your soils are by default having low phosphorus and then you apply phosphorus from outside, so response will be much higher in case your soils are low. But if your soils are high in phosphorus, their response to P application will be less. So that means that in this case, in the first case, the fixation of phosphorus will be less. In the second case, where you have high levels of phosphorus in soil and you again apply from outside, then the P fixation will be more. So response to P fertilizer on high testing soil is increasing, and it is important to maintain high soil P to support optimum crop production. Other nutrient interaction, particularly with the zinc and phosphorus have negative interaction. In general, if you increase the phosphorus levels, they reduce the zinc availability and vice versa. If you increase the zinc level, too much of zinc level in soil, it will reduce the phosphorus availability. I have seen one time a farmer applied zinc fertilizer at very high rate, very high rate, because say it happened 20-25 years before when people started using zinc in rice. So at that time, farmer was knowing that zinc is a new fertilizer and I should add it into the soil. He applied zinc at the rate of urea. What he was using urea rate, same rate was used for zinc sulfate. So you can see what could be the level of zinc in his soil. It was very high, and for 3-4 years, no single plant grew in his field because of no availability of phosphorus. So high zinc can suppress P availability, and high P can suppress zinc availability. But if they are at moderate level, at ideal level, they do not have problem. It is only when one dominate the other, then the problem comes. So adequate supplies of other plant nutrients tend to increase the absorption of phosphorus from soil. Calcium application on acid soils. If you supply calcium, it can increase phosphorus availability in acid soil. So it is interacting with calcium also. Application of ammonium form of nitrogen with phosphorus increases P uptake. This is very important point. From a fertilizer, then to apply the phosphorus fertilizer alone. So they are having positive interaction. Application of sulfur often increases phosphorus availability, particularly in alkaline soils. Alkaline soil, if you apply sulfur, it will reduce the pH and hence the phosphorus availability. Excessive zinc can affect P availability in alkaline soils. Now, certain crop factors also affect the availability. Type of roots, tap or fibrous roots. Wheat has shallow root system, while lucerne have deep root system. Explores deep into the soil. So larger the root growth, better is P uptake. And also solubilization. Most plant species can be infected with AMF. The role of AMF is already described to you. We have discussed soil organic matter. Soil organic matter generally increases phosphorus availability. It increases phosphorus availability. So soil high in organic matter contain considerable amount of organic P, which is mineralized. So organic matter is important, and microbial activity in the fixation as well as availability. Less fixation, more availability. So you can see here your available phosphorus with the help of microbes, it can go to organic phosphorus, or otherwise it can be mineralized by microbes and becomes available to the plant. Fixation can also happen. This process is immobilization. Conversion of available phosphorus or inorganic phosphorus into organic form is immobilization. It can be part of microbes as well as part of organic matter. Then available phosphorus can react with iron, aluminum, calcium in acidic and alkaline pH, and it can be fixed. So this is how these microbes are also important. In addition to supplying phosphorus, organic matter also act as a chelating agent, because ultimately it produces humus, which is chelating agent, and combined with the excess iron. So it can combine, means it can reduce the iron toxicity, thus preventing formation of insoluble iron phosphate. So that way your humus is useful. More the humus, the iron toxicity can be reduced, hence the phosphorus fixation. Heavy application of organic matter like manures, green manures, plant residue to soil with high pH not only supplies phosphorus, but on decomposition it provides acidic compound, increasing availability of mineral P. So you can see very interesting fact of organic matter, that it is beneficial for phosphorus availability under acidic condition by chelating the iron or aluminum, and at high pH condition, basic pH condition, it is reducing the pH and increasing the phosphorus availability. So for both pH, organic matter is really good. So overall, it increases phosphorus availability and decreases fixation. Humus extract from soils increase solubility of phosphorus. More the organic matter, more is humus. Formation of phosphohumic complexes. It can complex the phosphorus, which are more easily assimilated by the plant. Anion replacement of phosphate by humate ion. The coating of sesquioxide particles by humus to form a protective cover and thus reduce the P fixing capacity of the soil. So dear students, these were the important factors that affect your availability of phosphorus or fixation. If you have one or two quick questions, then you can ask, and then we will meet at 4. Yeah. So any question?